So ladies and gentlemen, I'd like to thank you all and welcome you all for attending today and giving up your time. Today we're talking about retaining walls. What I'd like to do first of all is for those people who are not users of the MasterSeries, just to take you through a wee walkthrough of what the MasterSeries is all about. And we have a modular approach to engineering. So for analysis we have frames and portals and simple beam design programs. We can then add on advanced wind analysis, BIM integration, finite elements and dynamic and seismic analysis. So that's your core analysis engines. We then have superb steel, concrete, composite connection and timber design that you can integrate into your frames, into your portals, into your simple beams, into your multi-story frames. And we also then have a range of standalone programs, although the PileCap actually can integrate in now as well as standalone. So what we're looking at today is this one program, retaining walls. So the nice thing about the software is it's modular. You only buy what you need. So if all you need is retaining walls, that's all you need. If all you need is masonry wall panels, that's all you purchase. So it's very simple. I'm just going to skip out of that. So starting up MasterSeries 2019, and I'm going to come straight in again with the 23rd of January version, and we're going to log into MasterSeries. So what have I got? Looking at this front screen, I've got my announcements down here of things that are happening, like today's webinar. I've got recent files, which we will use in a moment. Programs for your frames, your portals, your standalone connections, your retaining walls, which we will be using, and then your simple beam designers. We can also do the importing of IFC and Revit frames for our frame analysis. And then we have libraries and utilities. Resources is a very important one that's overlooked by people, particularly if you're learning to use the software. If you're learning to use the MasterSeries, don't just jump straight into a program and use it. With retaining walls, you'll actually get very far. It's quite a straightforward program. But what you have is access to manuals, and there we go. You can see there is a retaining wall manual, and it all looks pretty straightforward and tells you how to use it. And we then also have tutorials on the same basis. And finally, more importantly, is videos. When I go to videos, it takes me into our website and into the video guides. And this is where you learn to use the software. So let's look at getting started. You have your frames, you have your masonry, you have retaining walls. So we have in retaining walls 3 lovely simple programs to get you started, from just your basic concrete wall, your cavity reinforced masonry walls, and then your props and ties and things like that. So 3 simple programs to take you through. We also then have your full retaining walls list, which will list those plus others. And then you have your webinars, and you will probably find there's one about the retaining walls down the calendar list. So probably from last year we did a webinar on retaining walls, and this is where this webinar that I'm doing now will appear once we've edited the files and uploaded it onto the web. So an abundance of resources for you to learn to use the software. Naturally, you can also go and ask for support and submit support questions on the software. So I'm just going to come back out straight down to here, and let's get into, no more talking, straight into retaining walls. So programs, I can go and start retaining walls, and I can start a new one. But in my case, I want to take this last one that I was playing with and open it. And here we go. So what have we got? Well, we've got a pretty basic retaining wall. It's 2.5 meters high to the upper soil, 500 projection above ground, 250 wide, and it has a 600 of soil on the lower side, and we have water table at 1200 up. So everything else is fluid. These are the basic dimensions. We now need to decide how much of a heel and how much of a toe we want. So before we do that, let's go and look at our soil data. Back soil, 35 degrees, no cohesion, 17 kilonewton density, 0.6 submerged ratio, no over consolidation 1, and we're going to have the base is going to have a friction angular repose of 30 and a cohesion of 20. So very straightforward. And our soil, we will have two bearing pressures, one for the front and one for the back. If we put in a single value, we'll use the same, but we also have the option to have M1 and M2. M1 and M2 are for different loading conditions in the Eurocode design. We're going to keep it constant, so 100 kilonewton per meter bearing pressure throughout. What's our design code? Our design code in this case is EC2 concrete, EC7, which is the loading to Eurocode, and EC6 retaining walls. So all very straightforward. So now we've got our basic geometry. We want to step back and go to the wall, and all we need to do is first of all make the heel longer until it stops sliding, and I'm going to just increase that a wee bit more. So we're now getting it working. If you see the results, it's sliding, everything's unstable, wall stability, sliding, the whole thing's overturning and bearing. And as we moved up, we got to a situation where suddenly we're just about to get it, no sliding and no overturning, but the bearing is a problem and the steel is a problem. So let's continue on with our wall and increase that, and I'm actually going to make it 1250, which gives us a 200 base. So stability wise, this is working. We can see our stability, our sliding, our bearing pressure. What we need to satisfy now is the inner steel on the wall and the base steel top, this flexural steel here. So let's go to reinforcement, and at this point in time it might be worthwhile to decide we're using C3240 concrete, 500B steel, and we're going to go for 550 covers. So 10s at 200 is not good enough. Let's try 12s, and we're nearly getting there. You can see this capacity line. So we would need 16s at 200. So either 16s at 200, or we might consider 12s at 100 to be a solution. So I'm going to stick with 12s at 100, and then for the base I'm going to go down again to 10s at 100 is satisfactory. And that is now telling us that our reinforcement works, our stability works, our wall works. Very straightforward, very quick and efficient, and it is a very simple wall. So let's look at the different types of walls we can carry out and perform. So let's move across and look at the next one. This case, we've got two props. We've got a prop at base, which would get rid of sliding if we were up against something else, such as a house or another retaining wall. And we also have a prop up here to resist overturning. So we can see here we can get away with a lot less reinforcement. I would have thought we would come down all the way down to 10s. And Interestingly, the default was 12s. So 10s at 200 in both directions. Would we get away with a thinner wall? Well, let's go and have a try. Would we get away with reducing that wall? Well, certainly not 150. Let's put the cursor in there. 200. A 200 wall with 10s at 200 each direction would work because it's propped. And we can see our capacity line here for us. So that's our second type of wall. Still a reinforced masonry wall, sorry, reinforced concrete wall, but has now introduced props. A, to resist sliding, and B, to resist overturning. So some sort of basement in a building. My third type is where I start to get more fancy. Here's where I start to ramp up the complexity of the wall. Okay, it's no longer got any props, but it has a sloping soil, and it has two layers of soil, an upper and a lower, plus the water table. And if I look at my data, soil data, I can have the back soil, upper and lower layers. Obviously the upper layer can have tension cracks if it was a clay. Not that you really want the backfill in a clay in the first place, but you know, it's up to you. And then the lower is the lower soil, its height and even its slope angle if you want to make it a different slope. So 5 degrees there and 10 degrees up here. So they are different. And then you have your soil on your base and your soil in the front. So 1, 2, 3, 4 different soil regions that you can allow for and cater for in the software. And interestingly, as you move your water table up and down, you will see all these parameters start to change. So if I take my water table, there it is, and I start to walk that up, you'll see the pressure diagram starting to increase. And as I walk through, it's a wee bit faint here, but you'll suddenly see it getting higher and a wee bit of a kick and coming back down. I'm a great believer that even if it is drained, to allow for some water on the back of the wall. Now, we can, as you can see, have a tapered front or back, because we can say even and a tapered back by putting in 100 there, so nice and chunky and strong, but we don't need that. We can also introduce nibs, so I could say I want a 300 deep nib that is 250 wide. So 300 by 250 would probably be enlarged out to 350 to match what's coming up from below, and in it comes. We find that certainly to Eurocode and even to the BS, the 8002, these nibs are not very efficient because they don't contribute. They actually make it worse because you must take the pressure here on the active side all the way down. It's stopping here from an analysis point of view for the stem, but in reality it's the whole way down. And I could show, let me see, draw the partial diagrams. So I can do other things. I can decide what I want to draw, and I can draw the two diagrams with the two sides. Now we're not really getting anything here because this is the overdig. We have allowed for the overdig on our design. If you look at your defaults, the Eurocode says that you use 500 mil or 10%. We've got a surcharge that we've defined, and factors of safety in the BS, and then when you come into the Eurocode you have these factors of safety that you're using and bar sizes and things. So I am going to come back out of that. So I'm going to take off that nib. I don't like nibs and I don't believe in them. Take that out as well. If I now move forward, what's my next complex wall? And now we move into the masonry. In fact, maybe we shouldn't move into the filled cavity. We should have a solid masonry wall. Solid masonry wall is failing with steel, which it doesn't really have. So you'd turn around and you'd say that I do not have rebar in that, and we're now at 999. We would need a very, very wide masonry wall to make that work. So coming back, putting that back in again and going for an outer leaf and filling the cavity. So it's 100 cavity filled. We can see that we're at 2.4. What's our rebar? Our rebar at the moment is 16s at 100. So maybe let's move up a bit more. 20s at 100, and we're not really getting there. So we need to make it deeper. So how do we make it deeper? We make it deeper by first of all setting this to be 400, and then we tell it that it is in fact a 200 cavity. So the cavity is 200, and then this is 100. Or we could have had this outer leaf 200 and the cavity 100. So we could have gone 100 and 200, or 215 if you want to be even more accurate. So a 200 wide external wall, a cavity, and then internal shuttering. But there's no reason why we need to go for that. We can, with the correct wall ties between the two walls to act as permanent ties for the shuttering, work away with a 200 cavity here. And therefore we can see reinforcement wise 12s would work at 100. So we get away at 12s at 100 working in the cavity. There is no outer wall steel, it's all in the cavity, vertical bars in the cavity. So that is your reinforced masonry. Now the important thing to remember in the reinforced masonry is it's not really this that's the important value. It's important for the base, but not for the wall. For the stem, for the wall, what is important is the outer blocks. And we're talking 10.4. So if I increase that, you'll see the capacity line changing. So our moment doesn't change, but our capacity gets closer as we use weaker and weaker blocks. So 7 Newton blocks will not work. We would need more reinforcement because these blocks are your concrete compression. So the stronger the blocks, the better. So in my case, 10.4s will work fine with the standard mortar designation 1, 2 and group 1, and off we go. If we're dealing with a wall and we have particular blocks you want to modify the values, we can actually modify the FKs and the FKBs internally if we so desire, and we can even create our own block grade if we're using a block outside. So somebody's asking about factors of safety while I'm here. Abdul, there aren't factors of safety applied as such because it's the equilibrium of the Eurocode itself. The factors of safety come into play in the mobilization factors. In the Eurocodes, if I look at the soil data, or is it defaults, you'll see that we are applying these, reducing down different equilibrium factors of safety. So we're applying all these forces and factors of safety, and we're applying the mobilization to this to get everything working, and you have all the different values there default. So it isn't as such a factor of safety, it is working to the factored or unfactored loading and design conditions, and therefore then giving you a pass or fail on that. So it's quite interesting. So there you go, loading cases for the geometry and structural, and it's giving you the different loading factors that we're using. So geometrical design, so our geotechnical design, as you can see, our factors, and then our soil pressures, and then finally our structural design, and magnifying the at rest soil by the over consolidation and everything, which we left at 1 in the because we weren't assuming it was over consolidated at all. So very detailed, complex design. Okay. So far we've only looked at 4 different types of retaining wall. The next one is the stepped. Don't like it, but it works. As you can see, you need quite a distance because you're dealing with no reinforcement in this base. So you need to have quite a distance because you're dealing with the tensile strength of the masonry and mortar. So you need depth and weight and lever arm. And if I remember rightly, the old rule was 1 and 3. So you can see that that is roughly a 1 and 3 ratio. Maybe slightly less than 1 and 3. So the stepping is very straightforward. We just tell it how far down, out, down, out, down, out, and as we go. So if I said the first one wasn't 650 down but 450, it would then give you a heavier wall because it would all be containing more and more. So 675 I think was the step down, and we can see it now works. So we can see our curve and we're right close to that. Any deeper in this wouldn't have worked, and everything is fine. So stepped walls, we can step on the inside, we can step on the outside, it's not a problem. Not desirable these days. Reinforced masonry is far more desirable, but stepping for smaller work can be efficient. Now we're getting the complex loading. We can have loads on the soil, so such as a house, a strip found on a house of 10 kilonewtons at 2.5 meters out, but probably slightly more than 10 kilonewtons if you're dealing with a 600 wide strip. You'd probably argue it's about 60 or 100 kilonewtons. And then you have another one here at 900, so possibly it's 2 axles of a vehicle. We can also put loading onto the soil, or so onto the wall. And the interesting thing is, as long as this is on the soil, it's all being calculated and taken through manually, through the soil, using the wedge theory. So it's coming down through and down through the different substrates, whereas and only a portion of it actually gets applied. Whereas when we're dealing with the point load on the wall, this one here, it is fully loaded onto the wall. And then finally you're able to apply point loads outside the wall. So we did this because sometimes you may have some sort of bracket or gantry or something on the outside of a retaining wall that you want to cater for, and that would allow you to do that. And obviously that would allow you to put on a point moment as well onto that wall if you wanted to fiddle it using that value there. So we can actually apply these very, very straightforward loadings onto the wall and get our very complex pressure distribution diagrams and our bending moment. So you can see the kick coming from that point load and through, and then the capacity. So again, very complex, very straightforward. We're back to a simple retaining wall, but we're not. We're now back into the British standards, and for the British standards we also have the highway loading. So that would be BS and BS. Keep everything the same code. So highways, British and British. and you'd probably at that point in time, well, it is the highways. Yeah. So highways, and what we've got now in this one is if we look at our highway loading, we have some different load factors, and then we have the loads, and we are just designing this as a wall adjacent to a highway, and doing the checks on this wall. Very straightforward. The next one is the more complex when we're dealing with bridge abutment, where we're actually putting loads on the wall, and we're putting loads and saying whether they're HA or HB loads and applying them thus. So we can apply these surcharges over the flow, all over the soil and onto the wall abutment. And then you can see also you've got the abutment loading itself. So we're putting a 500 kilonewton, a 50-ton load straight onto the wall, and it's at 400, which sounds a bit strange. I would make that 200 or 100 to make it centered, and then that will be coming down through, and it's an HA load. And you can see all the different classes of loads that we can apply according to the rules of the BD documents. So bridge abutments, or not an abutment but just a ordinary retaining wall, but looking after the highway rules and load factors that they have accordingly. So again, very flexible and open and straightforward. So the next loading I have is a steephawk wall. Steephawk is one of those standard hollow blocks with notches in them in both directions that allows you to very quickly create a single width wall with rebar, no shuttering, no nothing, because it all looks after itself. And they come in three sizes: 200, I think it's 252 and 325, and we have all three of them built into the system. So here we go with our wall, and you'll see when we look at the reinforcement, it's automatically set at odd dimensions, 88 mil in and 10s at 200, with 6 at 225 as your distribution steel. And the nice thing about the steephawk is it's notched horizontally as well, so you actually get this distribution steel in, and there are no mortar joints. So I would highly recommend looking up the steephawk. There are others as well. So how did I do the steephawk? Well, I cheated because we've created them for you. So I want to add another design check, a design check 12, and I want to pull it in from my user database. So there's a 200. Let's go. There's a 256. There's a 325 wide steephawk retaining wall, and I've just pulled that in, and automatically it's come through for me with the default height and rebar in here, and you'll find it's using 20s at 163 millimeters apart. So I can turn around and say, well, actually my wall is going to be 4.1. Well, maybe not. 4 is exactly the height you are allowed, but we'll take that down and say it's 3.5, but we're then going to slope up the back of the foundation. How many degrees can we afford to go before the wall would get annoyed? And it's reasonable, so we could go up to about 18-20 degrees and it would still be fine. So with the steephawk you're nearly halfway there anyway, because we've pre-configured them to work, and you're just putting in a foundation base and go. So those are available for you in the system, and you can actually download them from our website and add them into your own libraries. So that was type 5. What we've got now is that's the steep hop we were looking at. Just coming near the end. This is a double propped wall. Somebody's just not drawing my props. Ties and props, that's better. Better if you draw them, you know what's happening. So you've got vertical load here, another one out here, and 2 props. So again, another construction of a basement wall, and it's very straightforward. And then finally, wee bit of playing around, a wee bit of lateral thinking. But this is how we would suggest you do a Gibeon. At the minute, the Gibeons can only be done to the British standard, so I just need to go and make sure that that is working to the BS for the concrete. Everything else can be Eurocode because it doesn't actually do anything. It just needs to know. And what happens then is when I come to reinforcement, you'll see the concrete tensile strength is 0, and I've no reinforcement in this. So these 3 steps are basically Gibeons, and I think, if I am correct, I put in the concrete density is only 16, so therefore that's your stone filled Gibeons is around 16 kilonewtons per meter cubed. So we are getting an interface tension, so our first wall, and where are we getting it? Important, it needs to tell us where we're getting it, and we're getting it at 2 meters from the base. So 1 meter, 2 meters, so it's at this interface, so therefore this length is not long enough. So what I need to do is to come along and make the first one 1200, but you wouldn't get 1200, so you'd be up to 1500, and then a meter and a meter. So that now will prove to work stability wise as a Gibeon. Now the trick is we do need to have a little bit of concrete base just for the software to work with, but it can do with a bit of this lateral thinking your Gibeon walls. Now last thing I want to look at before questions and answers is, you might have noticed in the invite we showed you a nice 3-dimensional picture, and that is because there's another way of doing retaining walls, and that is to create a finite element wall and base and integrate that into a frame analysis. And what we've got in 3D is a lovely steel building with bracing and everything above the walls, but we also have, because of soil, a retaining wall here and a retaining wall back here and here. So we have a retaining wall, and we could argue that this edge has not got any movement on it horizontally, so only vertical movement, which is what we've done in our restraints. But we've created these walls, and if we look at the individual wall and go to, remember, loading, FE surface loading, you will see that if I take this wall, I have put 1, here it is, 2, 3, 4 wall loads. So if I draw them all, you'll see they're all at different intensities because they're different heights. You could argue that they're coming down gradually, and you might want to do some sort of line across here and then just do that as being your wall. That's exactly what I did on the far side. If I go to this wall instead, you'll see that I actually created a line between the top and bottom and said that's the soil height and that's the soil pressure up here and here, and it's all linear, so therefore we get the higher hydrostatic and soil pressure over here. And we did the same on the back. So what we're able to do with that then is, having analyzed it, and I'm hopefully already analyzed it, going into graphics, we're not looking at our bending moments and everything on our main structure. What we're interested in is the shell elements. And if we come to the shell elements, I'm stealing a wee bit of thunder here already. If we look at the MX moment, you'll see that it's pretty small. It's just giving some under each of the column point loads. If you look at the MY, it's sort of similar. It's a wee bit of a MRX again, but those are not important. What's important at this level is the MRX and the MRY. The MRX and MRY moments, and you will see that the values that we have, there's tiny little increases between these, and that's just a resolution point. It's not really important at that corner to an extent. So, but what we're really interested in is first of all the Y displacements, and if I put this on plan, you'll see that the inside is going down and the outside is uplifting, as you would expect. A little bit of rotation because my foundation on my surface, my horizontal surface, had a subgrade modulus with no tensile strength, compression only. So that's going down and up due to the very high wall giving us an overturning, and likewise these are going down and these are just doing nothing much. So a little bit of a down and just a little tiny movement here. So that's quite interesting. Y displacements, more importantly, is your X, which is pushing the walls in this direction. So you can see this top going this direction and this top going the opposite in this direction. So moving in by 1-2 millimeters. Obviously this is under ultimate. And then more dramatic is the opposite direction. This wall here moving in the Z axis. But you've already checked everything, you've looked at the overturning, you've looked at everything, and you will have the ability to come along and look at your reinforcement then. 500 grade 35 is the cube, and now you'll see that most of it uses nothing. So we can see there's a massive coloration of nothing at a tiny point. So what we would do is you come along and say, well, let's just say, let's put our maximum value in as 1000 and apply, and then you see where we need the reinforcement in the XX, and you can see we need it in here, and we're needing more than 393, but we can go ahead and design that as we desire. So that's a little extra for you if you're interested in doing retaining walls inside buildings. Okay, can you do inclined walls? Oh, absolutely. You can have some real fun if you really want to with the wall, because you can say that you want it to be, let me get this right, I'm going to make this 200, and then I'm going to put this one in as minus 200, and I now have a sloping wall that has an additional restoring moment, which is quite clever and quite useful sometimes, but in this case also is putting an additional base reinforcement requirement into the steel that's messing that around. But yes, so you can now go and have that such, and yes, you can. Can you apply a partial UDL on the wall? Interesting question. Let's look at loads. Line loads, they're pretty straightforward. You have a value and a point, and somebody's not drawing your diagrams. So going back to loads, so there's your point loads. Let's get rid of point loads. Line loads, absolutely. You can say where it stops and starts, so that is a partial UDL. Obviously everything is per meter run of wall into the page. Now wind load, if you have an upstand like you have here, you can apply a horizontal surge or a wind load. So I can say that I have 1.2 kilonewtons pushing back over. It's always in the detrimental side, never in the beneficial side. And I can also say that we've got a barrier above this, erected, and therefore we're taking our standard 10 kilonewtons at 850 above the barrier again as well. So we're taking that load and again overturning it. So we can apply both wind and a horizontal load, a surge force on the wall. Counterforts and buttresses, piers, that's what they're called. So let's get back to the wall. Let's get rid of this silly sloping and over sloping. Let's go now come and say we want to come to piers. Yes, you can go for stiffened piers and have counterforting and then spanning in both directions. So absolutely, yes, you can do counterforts. Can you have a pier on the opposite side? Ooh, yes, you can. Absolutely. Do that pier on compression outer face. So the piers are in compression rather than tension. They work better. This is your main tension steel, more spread out, less problems. That may look less pretty. So last thing I want to finish with is coming back. Let's get rid of the stiffening. Let's get rid of the additional loads. If you have a wall that works and you're happy with it, you can then take that and you can export it with some basic parameters and say, yes, we're going to do a 8 meter length of wall, and we can export that as a DXF, and in it comes, and we're going to load AutoCAD, and there you go, loading AutoCAD. We don't need this little CAD layer thing, so there you go. There's your details coming up, and it's probably the thickness of one of these for the bars is too small, is what the problem is. And then there's your starter bars and your main bars. Now at this moment in time, the main steel and the starter bars is all the same. Certainly what you can do is you could curtail your reinforcement to have half of it stopping short, and as long as you're above the point at which it's no longer required, or only half of it's required, that will be okay again. If you load two walls into the one drawing, is the schedule revised to include the two walls? No. You would be doing two separate schedules for two different walls, and to be perfectly honest, you might want to do that so you don't end up getting the two sets of rebar mixed up. But no, it's a one-off at a time scenario on that. So that's your walls exported out into AutoCAD, and having done the export, we would be able to also do the schedule, and you can see that you've got your 7/9, 8 meters long, so your distribution of steel is 7/9, 50 cover each end, and obviously your weight per element is a total of 0.9 of a ton of rebar in that design, and that's all done. That's all part of the MasterSeries retaining wall design program. So if you want to try it, you're most welcome to try the software, and all you have to do is come along into the MasterSeries, and it's probably easiest just to go to the product, retaining walls, view the product, and from there select start your free trial, because that means it selects exactly what you're needing. So if I put in my details and select that I am a consulting engineer, when I go to next, you'll see that it's automatically selected retaining walls, and off you go, and then off you go, and you will shortly get a response back with a download link to try the software for 14 days. Now the 14 days is actually 15, but don't tell anybody. So you're more than welcome to try that. You're more than welcome also to have a personal demonstration of the software. If you want a one-to-one demo of using the software, even if you've downloaded it and want a wee bit of guidance, so you can say book a demo, and off you go and just book in a demo of retaining walls, off you go, and with myself or Andras, and choose when you want it. And obviously days and times are available, different times each day. So please, ladies and gentlemen, feel free to download and try the software. Any questions, just email myself, that is Tommy at MasterSeries.com, and if it's very technical, I'll pass it over to the technical guys and get an answer for you. So ladies and gentlemen, I'd like to thank you all for coming along, and I'd like to say it's the first time I've ever actually finished on time. We had a massive turnout. It is, I think we had nearly 400 registered for the webinar, from countries from as far afield as Australia to Zambia, so from A to Z. And we had existing users, PowerPad users, and non-users. The last thing I want to talk about is what is PowerPad and what does PowerPad give you. The PowerPad version of the Masters retaining walls is a limited version. So if I go to products and into PowerPad, you'll see that there is a little retaining wall icon. Did I click on that? Yes, I did. And you'll then see that it talks about the different features, and there's your retaining walls, so you can see doing retaining walls. So you get reinforced concrete or plain masonry in the PowerPad version. You don't get reinforced masonry, you don't get additional loading or highway loading. So just the simple standard walls. There's no problems upgrading to a full version at any stage. If you are a PowerPad user but would like the fuller version of the retaining walls, that comes at a discount because you've already got part of it. It is a standard discount at any stage. So typically people do upgrade to the software. So again, thank you everybody. Have a great day, have a great week, and next webinar is in March, and it hopefully will be exciting. If you want to stay in contact and receive invites directly on any of the webinars, just come down to the home page and then just go to subscribe to newsletter, and that will get you automatically every month the invites to the webinars plus other information as required. So for the last time, thank you very much and have a great day.